Okay, so in this example, we had already studied two special cases. It is C, because it is accelerating with constant acceleration, which means its velocity is a linear function of time. The velocity goes like t multiplied by some constant. The kinetic energy is proportional to the velocity squared, so it is proportional to t squared. It is this one. It is not B. B just assumes that the kinetic energy goes linearly with time. It is not E. It just assumes that the acceleration is getting smaller as it moves, but acceleration is constant. And it is not D. Kinetic energy cannot be negative. You don't need to write an explanation in the quiz. You could have just given a paper with your name and number C. Okay, so yes. Why not B? Okay, so B, it is just a linear function. So it says that the kinetic energy is proportional to the time. But we know that since it is dropped to Earth from a height, it is a motion from close to the Earth, so it's motion with constant acceleration. So velocity goes proportional with time. So if you would plot the velocity versus time graph, the speed versus time graph, it will be linear. This is the speed versus time. Now the kinetic energy is equal to 1 over 2 m times v squared. This is 1 over 2 m. The velocity at a given time is g times t. All of it is squared. So the kinetic energy is 1 over 2 m g squared t squared. So this, a linear graph, just means that if at t equal to 1, the value is a, at t equal to 2, the value is 2a. But I know that if at t equal to 1, the kinetic energy is 1 unit, at t equal to 2, the kinetic energy is 4 units. So if this is the velocity, if I would plot the kinetic energy diagram, if this is the kinetic energy has this value, k0, at time t equal to 1, it should have the value 4 k0 at time t equal to 2. So it should go like this. And it is therefore C. Well, that is the closest one. Now let us look at this. We had already looked at the cases when the two masses were equal. Yes. Well, okay, so from a 10-meter height, it will not reach terminal velocity. If it reaches the terminal velocity, what will happen is, well, let me plot it over here as a function of time, the kinetic energy. So first, it will move with constant acceleration. So it will move like this. It will start like this. When it reaches terminal velocity, its speed is not increasing. So it is kinetic energy is constant after it reaches terminal velocity. So let's say at this time it reaches the terminal velocity. This will be the graph after that time. So in between, it will probably make something like this. This will be the graph, if you threw it from such a height that it reaches a terminal velocity. Well, in such cases, when you want to draw graphs, when you just want to do sketches, you just look at the limiting cases. I know how it behaves here, and I know how it behaves here. In between, if the details are not important, you just connect them through a smooth curve. And this will give you an idea of how it behaves. Any other questions? Can we continue with this? Thank you. So before we continue, we cannot continue with this. I have a small announcement. From the education department, there was a request for a survey. It was a survey to be conducted on students that have brothers or sisters. I have like 180 surveys here. 2 of your friends had already picked them up. Can you stand up? Yes. So these 2 friends have no, not you. Only those 2 have the surveys. They have all the surveys. Each one has around 40 surveys. So if you are interested in filling out the survey, you should just contact them. Well, my point of view at looking at these things is this survey is a research for a graduate student in the education department. And I do think as scientists, as people who are supposed to do research, we have to support people who are trying to do research. So that's why I brought it here. It is voluntary. You don't have to do it. You are not putting your names on the surveys, so it will be completely anonymous. If you want to fill that up, it will take you around 10-15 minutes. You can just pick it up from your friends and then return to me. Either you can throw it in my door, leave it in my office, or bring it on Thursday in the class. Thank you. Okay, now we can start this one. Now we had looked at the cases when the first ball was, the balls were at equal weight. That was the example we had here. When the second ball, the target was heavy. It might also happen that the first mass is heavy. So you can just imagine you are moving, you are quite heavy, and there is a feather on your way. So you are this is you, M1, and there is a very light target of mass M2. When they collide, well, the formulas already tell you the result. If M1 is really heavy, then the velocity of the first mass after the collision is just V1, it doesn't change. And the velocity of the second mass, though, it is twice your velocity. Now, another example of this is if you are playing football. You have your feet and the ball. That's the collision process. Your feet is, if you are not have a professional football, the balls are quite light. So you can just consider it at this limit. So this already tells you that the velocity of the ball when you hit the ball will be twice the velocity of your foot. So the faster your foot moves, the faster the ball will be moving. Now this factor 2, why? Why do we have this factor 2? I mean, in these cases, when the masses were equal, we kind of had we have an intuition, we have experience, we had just made a demonstration that after the collision, what happens is that the first mass is at rest, the second mass starts moving with the initial velocity. This we have experienced when the target is really heavy, you just throw a ball on the wall doesn't move at all. Or if you just hit a very heavy object, the heavy object will not move, you will just bounce back the heavy object. But this we don't really have much experience on that. And we don't really measure the velocity of very small objects that we hit. But we can interpret this in terms of the first special case. Now, the third case and the first case are, in fact, the same cases. Now, what happens in the third case? Well, in the first case, we have a very heavy object, a very light object before the collision. This moves with velocity v1. After the collision, it keeps on moving. No, hold on. It's the opposite one. The first case is we have a small object which moves with velocity v1, hitting a very large object, which is at rest. After the collision, the large object is still at rest. The very small object is moving with velocity minus v1. So this is what happens in the first case. Now, if you look at the third case, initially we have a very large object moving with velocity v1, and now we have a very small object. So this is what we are studying. But remember, when we were discussing the reference frames in the coordinate axes in the first few weeks of this semester, we said that which reference frame you choose is completely arbitrary. You can choose any reference frame that you like. So instead of considering this problem in this reference frame, in which this one is moving with constant velocity, this one is at rest, we can just move to a reference frame which moves with this one, along with this one. So rather than you throw your ball, you throw this heavy object, and you keep on walking with that object. So that object, relative to you, in that case, will not be moving. It doesn't have any speed. So this system is the same as this system. They are identical. They are just in two different reference frames. In this one, I have this large object, or if you are playing bowling, you have this heavy bowling ball. You just throw the bowling ball and look at the ball just go away. That is our first case. The third case that we are studying, we have a heavy bowling ball that's moving with some velocity. Or you can say that, okay, you have this heavy bowling ball, you throw it, but as you throw it, you start walking with the velocity of the bowling ball. So the bowling ball doesn't go away from you. The position of the bowling ball relative to you doesn't change. And since you are moving at constant velocity, your reference frame, in this case, is an inertial reference frame. So I can study all this phenomena in that other inertial reference frame, in which, okay, this is the first reference frame where the bowling ball is moving with the velocity v. Our target is at rest. This is the other reference frame, my reference frame, where the bowling ball is at rest, but the target is moving towards me with the velocity v1. The velocities here are related to the velocities here through the velocities here, let's call it down v prime, are nothing but the velocities in that reference frame, whatever the velocity, minus v1. Since this reference frame is moving relative to this reference frame with the velocity v1, if you just review the section on the relative velocities, the velocity in the second reference frame is given by the velocity in the first reference frame minus v1. So that is why this is at rest, because initially it was moving with velocity v1. v1 minus v1 is 0. This is at rest. And this was at rest, so this was 0, 0 minus v1. In this new reference frame, this has velocity minus v1. Well, after the collision, this is the first case over there when the target is very heavy. After the collision, what happens is this is at rest, but the target starts moving with velocity v1 in the opposite direction in the second reference frame. Now, if I want to go from this reference, this is after the collision. Now, if I want to translate this picture to the original reference frame, what should I do is, well, this also means that the velocities in the original reference frame is equal to the velocities in the second reference frame plus v1, plus the relative velocity of the second reference frame with respect to the first reference frame. So this is at rest. So in the original reference frame, it is moving with velocity v1. So in the original reference frame, this one is moving with velocity v1. And this one is moving with velocity v1 plus v1 twice v1. And that is what we obtain in the third case. So if we just review what is going on. We have this billiard ball. I have a table tennis ball somewhere over there. So I throw this bowling ball towards the table tennis ball, and I watch what is happening. So initially, the bowling ball had this velocity v1. It was at rest. So this formula already tells me that when the bowling ball hits the table tennis ball will start moving with a speed twice the speed of the bowling ball. This is one picture of this is one way of looking at this process. Another way of looking at the same process, as I throw the bowling ball, it starts moving with velocity v1. I also start moving with velocity v1. I'm moving with the bowling ball. So the bowling ball is not moving relative to my position. But the table tennis ball is approaching me with the velocity minus v1. In the other reference frame, I'm approaching him, but in my reference frame, the ball is approaching me with the velocity minus v1. Well, in my reference frame, in which I'm moving with the bowling ball, well, the table tennis ball just approaches with minus v1. It is very light, so after it hits the bowling ball stays at rest. It doesn't start moving after the collision, but the bowling ball just changes its direction. So it starts moving with velocity v1 in that direction, in my reference frame. Now, if I had a friend over there standing, if I would have told him that, okay, the bowling ball after the collision is moving with velocity v1 away from me, he would say, okay, the bowling ball is moving with velocity v1 away from me, but I am moving away from him with velocity v1, so the bowling ball is moving away from him with velocity twice v1. So that is why we have the 2 over there in the third case. Okay, so do you understand that in my reference frame, when I'm moving with the bowling ball, after the collision, the table tennis ball is moving in that direction with velocity v1. I'm moving with constant velocity v1. And the table tennis ball is also moving with velocity v1. So what does that mean is, in 1 second, I move in that direction by v1 meters, v1 times 1 second meters. The ball, according to my friend over there, the ball has moved away from me v1 times 1 second meters. So according to him, the ball has moved by twice v1 times 1 second in 1 second. Or you can say, if I'm moving with 5 meters per second, in 1 second I would move 5 meters. If the bowling ball is moving according to me by 5 meters per second, so the bowling ball goes away from me by 5 meters in 1 second, so my friend standing there will see that the table tennis ball had moved by 10 meters in 1 second. There are no forces. The only force acting on, in these cases, the only forces we are interested in are the forces that act during the collision, when they collide. Of course, there is a gravitational force, but that will create an acceleration in the downward direction, which we are not interested in. Yes? Okay. Is there a particular thing that is confusing you? Any one thing that is confusing you, or you are confused in general? Okay, I need another volunteer. Well, you will hold the table tennis ball. And this is our bowling ball. You just stand over there, somewhere over there. So, you are here. I'm one. Okay, this is the bowling ball, and you throw it. Okay? So you throw it such that in 1 second, this goes away by one step. So 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and so on. So that is what you observe. Okay. In 1 second, I am going away from you by 1 step. The bowling ball is moving away from you by 1 step. Now, when I look at the table tennis ball, though, since I am moving with the bowling ball, the table tennis ball is moving towards me by 1 step every second. Okay, so in my reference frame, the velocity of the table tennis ball is -1 steps per second. Now, this is very heavy, So I'm moving with 1 step per second. I hit the table tennis ball, and the table tennis ball hits me. I'm at rest. The bowling ball is at rest. The table tennis ball comes and hits me by 1 step per second, after which the table tennis ball starts to move away from me by 1 steps per second. After once, let's say we have collided. After 1 second, I have moved 1 step, but the table tennis ball had also moved away from me by 1 step. So the table tennis ball had moved from its original position by 2 steps. So in 1 second, it has moved, according to you, by 2 steps. So in your reference frame, the velocity of the table tennis ball is 2 steps per second. Okay? Thanks. Now, one of the questions that quite often arises when you are solving questions is, which reference frame should I choose? Arbitrary. Whichever reference frame you choose, if you do the things properly, they should all give the same result. So we have this case, this problem, for example. We studied the same problem in 2 different reference frames, and both results agree with each other. They should agree with each other, because reference frames are things that we invent. It's not something that nature cares about. So you are completely free to choose whichever reference frame you like. And if you know the answer in one reference frame, then just use that. And then you can just go back to the other reference frame. That is what we did over here. We were studying the same problem in 2 different reference frames. And I had this case, but you can show that this third case is nothing but the first case in another reference frame, in the reference frame which is moving with the bowling ball. I know the result for this case. I can just use that, translate it to this reference frame, and I could have obtained this factor of 2 without taking these limits. So, and yeah. Let's just do some questions. So I'm just standing at the side of a cliff, uçurumun kenarında duruyorum, and I just drop some mass down the cliff. So what is the change in the momentum of the earth and the cliff? After you answer, just make sure that your neighbor also has the same answer. Okay, so somebody who says that it was C, why do you think the answer is C? Momentum of the system doesn't change. So somebody who has given an answer A, why do you think it is A? So, okay, any objection to that from the C group? So she says that the velocity of the object is growing because there is a force acting on it, so the momentum is increasing. Any objections to this? Yes? So, any defense from the A side to that explanation? He said that, okay, there are two forces, the force acting on the Earth and the force acting on the mass. So the change in the momentum is proportional to the sum of these forces, but the sum of these forces is 0, so the momentum cannot change. So any objection to this one? Or somebody else who had answered A, do you still think it is A? Okay. So the kinetic energy is increasing, so the momentum is increasing, you mean? So that's a defense. He's saying that the kinetic energy of the system is increasing. So the kinetic energy of the system is constant. Yes? Well, okay, so that is basically the idea. The momentum of the whole system is constant. It is true that the velocity of the object is increasing because there is a force acting on it, so it is accelerating towards Earth, but at the same time, Earth is accelerating towards that mass because there is a force acting on the Earth due to that mass. And these two changes, they just balance, and the net force stays the same. Net momentum, the total momentum stays the same. Now there was another thing. The kinetic energy is increasing. Well, let's discuss that one. I mean, we had used the word internal energy from time to time, but we didn't really specify what we mean by internal energy. Now we will define in more detail what we mean by the, well, let's discuss what we mean by the center of mass. Now, when you consider a system of objects, you have many masses. Mi has the velocity vi. Then the momentum of the ith object is just mi vi. And when we look at the change in this momentum, well, this will be Newton's second law just tells me that the change in the momentum of this object is nothing but the total force acting on my object. Well, the total force acting on the ith mass, I have various masses, they might have two sources. Either the forces might be due to some other mass in my system, so I consider this as my whole system, m1, m2, mi. There might be a force acting on the ith mass due to the jth mass in my system, and all of the other masses can exert a force. This might exist, so you can just imagine a system of gravitating objects, or you can just take, for example, the Earth and the Moon system. We have the Earth and the Moon. They both exert force, gravitational attraction on each other. So this is the force that they exert on each other. But there's also the force, if this is the, if I'm talking about the Earth, there's a force acting on Earth due to Moon, but there's also a force acting on Earth due to the Sun, the other objects that I'm not considering in my system. So let's call this the external forces. So this will be the rate of change of the momentum of the ith mass. Now, if I define the total momentum of my system as the sum of the momentum of each one, here I'm basically doing two things. We had already discussed the example of two masses. Now I'm generalizing it to many masses. Plus, I'm also adding the possibility that there are forces that might be acting on my masses due to other objects. Due to the third mass, the fourth mass. If I have a system of 2 point masses, I might have a third mass somewhere over there acting with forces on these two. Those I denote by these external forces. Now, if the total momentum is the sum of the momentum of each one of them, the rate of change of the momentum of the whole system is nothing but the rate of change of the sum of the rate of changes of each one of them. But this one, I know that it is given by this expression. So here I have a complicated sum, a double sum over I and j, Fij plus I Fi external. So these are all the internal forces that my masses exert on each other. The first mass exerting on the second mass exerting on the first mass exerting on the third mass exerting on the first mass. I'm just summing all of those pairs. But those pairs, I know that they form action-reaction pairs, so they just sum up to give me 0. So if I consider the force acting on the first mass due to the second mass, this is F12. Then I have the force acting on the second mass due to the first mass, F21. Since they are action-reaction pairs, the sum just gives me 0. So this term, this is a sum over all such pairs, is just 0. This is the external force acting on each one of the masses, but this is nothing but the total external force acting on my system. So the rate of change of the total momenta of my system is nothing but the total external force acting on my system. Well, this is just like the Newton's second law applied to the whole system, not to point masses. But for point masses, we already know that the rate of change of momentum with time is the force acting on it. This is what Newton tells us. That law is valid for point masses. But we have just proven that this force is also valid for systems made up of many particles, as long as we interpret this momentum as the momentum of the whole system, and the force is the total force acting on the whole system due to external effects. Because if I consider this system, there are internal forces and there are external forces. Internal forces do not create any change in the momentum. It is only the external forces that change the momentum, the total momentum of the system. Now, the momentum in general, for point particles, we had defined as the mass times velocity. We can repeat the same thing for the total momentum. The total momentum we will define as the total mass of my object times some velocity. This is the definition of this center of mass velocity. Here we are defining the velocity of the center of mass. Now, but the velocity is usually, well, for point particles, we always define the velocity as the rate of change as their position. We do the same thing. Here, the velocity of the center of mass, we define it as the rate of change as the center of mass position. So the velocity of the center of mass is nothing but 1 over the total mass of the object times the total momentum. Now, if you just replace the momenta in terms of the masses and velocities, I can write the velocity of the center of mass as the time derivative of this combination, which I define as the center of mass position. So the center of mass position of an object the center of mass of an object, of a system of point particles, is defined as 1 over the total mass times the mass of each object times the position of that object summed over all my point masses making up the system. This is how we define it. In fact, up to now, we have been using Newton's laws for extended objects, not point objects, without really any justification, because this law is in fact valid for only point masses. But now we have the proof that what we have done is justified, as long as the momentum is the total momentum of the object and the force is the net external force acting on my object. So we can use the Newton's law even for extended objects. Now, let's just apply this. Now, if I have, for example, this object, it is moving. It can make a complicated motion. I can just consider it as made up of small parts. For the simple case, let's just assume that I have two objects, just like the earth and the stone we threw off the cliff. Now, instead of talking about the velocities of the earth, this is the velocity of the earth. Now, V1 and V2, you can think of them as the velocity of the earth and the velocity of the stone that we throw. Instead of working with V1 and V2, we can talk about the center of mass. Well, when we are talking about extended objects, that is what we had done. We were working with the center of mass coordinate. The center of mass and the relative velocity. Now, if we work with the center of mass and the relative velocity coordinate, or the center of mass velocity and the relative coordinate, you can solve for each one of the velocities, V1 and V2. And at the end, this is what you would obtain. So you can just go over the algebra, and then you will see that the kinetic energy of this two-mass system is just 1 over 2 mv center of mass squared plus 1 over 2 mu. Mu is just some constant, mu times the relative velocity squared. Now, if you look at this, again, let's just consider this one, as it is flying. It has a center of mass velocity. So we usually, when we want to talk about the kinetic energy of this thing, as it is flying in the air, the kinetic energy, we just define it as its mass times its velocity squared. This is what we call the kinetic energy of this extended object. But then there is also this possibility of this term. As this thing is throwing, it might be rotating, But if it is rotating, it just means that different parts have non-zero relative velocity. So each part is moving relative to each other. So there's a relative velocity. And so there's also this part in its total energy. This is usually what we call the kinetic energy of an extended object. And this is what we call its internal energy, the energy due to the relative motion of its internal parts. Now, if you go back to our example of the Earth and the dropped stone, we know that as the stone is dropping down, its kinetic energy is increasing, but what is increasing is its internal energy. Internal energy of the mass, the Earth plus the stone system is increasing. The center of mass kinetic energy is not increasing. The center of mass kinetic energy is constant because the center of mass kinetic, the change in the center of mass velocity, well, the velocity or the change in the total momentum of the system will be caused only by the external forces. Now, defining my system as the stone plus the Earth system, there are no external forces acting on my system. Since there are no external forces acting on my system, the center of mass velocity and the total momentum of the system is also constant. It doesn't change, although the internal energy of my system is increasing. Any questions on this one? So the answer is stay the same. It doesn't increase, well, the momentum of different parts is changing as the stone is dropping, but the momentum of the whole system, the Earth and the stone as a system, it doesn't change. This is a similar question. Well, this is kind of, you have probably heard of the jokes about asking you what happens if 1 billion Chinese jump at the same time. So this is what happens to the Earth as you jump. One different ingredient here is the friction. So how will the friction affect anything? How will it affect? So let's start with somebody who has said A. Why A? So, there is no kinetic or potential energy. The momentum, there is no momentum of the system. At first, there is no momentum of the system, okay? The momentum increase. So the answer is, if I understood it correctly, initially there is no momentum, everything is at rest, but then the kinetic energy of the system is increasing, and hence there is momentum. So the momentum increases in the downward direction as you rise. So you are jumping up. This is what you do. Okay, so as you rise, there is an increase in the momentum. So that is an answer A. Okay. Okay. Do you have any objection to that? Okay. So he's saying that he still insists that energy is increasing, so there is momentum change. So why do you think that increase in energy is a means a change in the momentum of the system? So, okay. If you think of what? Grenade, okay. Even in that case. So he thinks that the momentum is changing. Okay, now, so you are kind of blocked. Okay, Doa? So he's saying that, okay, each part has a momentum. The Earth has a momentum in the downward direction. You have a momentum in the upward direction after you jump, right after you jump. So the net momentum after you jump is still zero, although each part has a momentum. So you have well, anybody else who's supporting A, who will support your friend explicitly? Yes? Okay, so as you jump, there is a normal force. The Earth is acting you with the normal force. So, hold on. So, the force is acting on whom? The normal force is acting on which object, me or the Earth? Me or Earth? Or both? Okay. The changing. So your friend is saying that, okay, there are forces in the system. Earth is acting on me with a force. I am acting on Earth with a force. But the total system, when we are talking about the change in the momentum of the whole system, we are summing over all the forces. These two forces, when we sum them up, they give zero. So there is no momentum change. Is that what you are saying? Okay. So that is what the claim of your friend is. So your answer was A, B, or C, or D? A, so okay. Okay. I'm If there is force, there is momentum change. Okay. Your answer is D, dissipate because of friction, okay? Okay. So you say it will be, by the way, the friction there you are talking about is probably friction due to air, right? Okay, so when we are talking, we are saying the Earth contains the air also, so you are also taking that into account, right? Okay. Which other friction? Okay. Okay, so he's saying that there is when you jump up and down, there is air friction plus the Earth is being compressed a bit. There will be friction due to that compression. So he's saying that when he says that it will be dissipated by friction, he's taking into account all these kinds of friction. Okay, so his argument essentially is that, okay, when I first jump up there's probably no change in the momentum of the whole system, but due to friction, some of that momentum will just dissipate. So that is your the friend of your answer. Okay, any other comments? Well, they were probably not convinced by my answer anyway. So okay, somebody else. First, let's give a chance to somebody else besides Doa, and then we will come back. You are an A guy, C guy, or a D guy? Okay. Now you are a C guy. Okay. You don't agree? Yeah, where are all the other A guys? So you are still saying A. Okay, so there you have a lie. Okay, so let me give you my answer. You don't have to be convinced. We should continue until you are really convinced. First of all, the definition of momentum or the change in the momentum has nothing to do with energy, potential or kinetic energy. Of course they are related, because momentum is related with velocity, which is related with kinetic energy, which can be converted to potential energy. So what is happening here is, as I ignore friction for the time being, just for the time being. Let's add the friction later on. Now, when you are jumping up, there's the only force between you and Earth is you are pushing Earth down and the Earth is pushing you up. So your moment, you are going up as you are jumping up. Your you have a momentum in the positive. Initially, let's say you don't have zero momentum. You have zero momentum. Earth has zero momentum. But when you jump up, you have an initial upward velocity and hence an initial upward momentum. You agree? Yes, I have an upward momentum, but I am pushing Earth down. Since I'm pushing Earth down, Earth had gained a downward momentum. Why not? I am pushing Earth down, right? So when you are exerting a force on an object and the object moves under, if that is the only force exerted on an object, and the object is moving under the influence of that force, the object will acquire a velocity and hence a momentum. So when I'm moving up, I'm pushing Earth, so Earth is accelerating downwards. Now, in the initial reference frame. So we are in this reference frame. So I have this reference frame. Here I stand. Here is Earth. Then I jump up. This is my reference frame. I do not change my reference frame. I'm here. I'm up. And the Earth is now down. I have an upward velocity. Me. The Earth has a downward velocity. So I have an upward momentum. The Earth has a downward momentum. Initially, none of us had a momentum. After I jump, we both have a momentum in opposite directions. So the total momentum is 0. Initially, the total momentum was 0. Finally, the total momentum is 0. Okay, question over there. What do you mean sufficient force? Why not? I mean, let's just calculate how much the Earth accelerates. So when we are jumping, let's say that I gain a velocity of 5 meters per second. Okay? Let's just say that my velocity, right after I jump, my speed is 5 meters per second. I'm around 70 kilos, so my momentum is 70 times 5 kilograms meters per second. 350 kilogram meters per second. That is my momentum. My claim is that the Earth also has the same momentum in magnitude. So Earth has this momentum of 380 kilograms, 350 kilograms meters per second. Let's calculate the speed of Earth. This is the mass of Earth times the speed of Earth. This is what I claim. Well, what is the mass of Earth? Do you remember from the exam? Ten to the power 20. It should be something 10 to the power 24 kilograms. This is the mass of Earth. So right after I jump, the velocity of the speed of Earth is about 3.5 times 10 to the power minus 22 meters per second. This is the velocity of Earth after I jump. This is, in a sense, you can say this is the change in the speed of Earth. Now, if the Earth would keep moving with this speed for an hour, the displacement of Earth would have been delta R will be VE times 3,600 seconds. This is how much the Earth would move in 1 hour if the Earth kept moving at that speed. Well, the Earth doesn't move at that speed because I claim that the moment I land back on Earth, the velocity of Earth will be 0. But let's just assume that I jump up with this velocity and somehow some space engine just takes me away to the space so I don't fall back. And the Earth keeps moving with this velocity for an hour. So this will be, the displacement of the Earth would be around, let's say, 10 to the power minus 18, something like this, meters. Well, the radius of an atom is 10 to the power minus 10 meters. So in 1 hour, the displacement of the Earth will be much, much less than the radius of an atom. This is the typical size of a quark in the nucleus. Well, at least we know that the size of the quarks is less than that. We don't know the size, but it is less than that. it doesn't mean that the velocity of the Earth is zero. It is still, it has a finite velocity, but it is so small that we cannot observe it. But the mass is also so large that even for such a small velocity, it can have a momentum that is equal to my momentum. So this is why the velocity of the Earth after we jump, it is so small that we think that it is not really moving, but it is actually moving. Okay, now, could I convince you that you are no longer an A guy? So any A person here? Now let's come to the friction case. What happens with the friction? Yes, Doğa. Well, but still, what you are saying is, if it decreases as I'm rising up, it will increase the momentum as I'm falling down, so that there will be no change. That is what you are saying. But my claim is, even if there is friction, the momentum of the whole system will never change, neither as you are increasing nor you are falling down. That is my claim. Why doesn't it change? As I'm jumping up, let's just consider only the air friction. I'm jumping up. I have an upward momentum. The Earth has a downward momentum. The friction is acting on me in the downward direction. So it is increasing my momentum in the downward direction. But at the same time, the friction is a friction between me and Earth. Air, I'm just thinking of air as a part of the Earth. So I am exerting a force to the Earth in the upward direction. So my momentum is increasing in the downward direction. The momentum of the Earth is increasing in the upward direction. So the net change in the momentum is still zero, even if there is friction. Okay, so when I fall down, you mean? Okay, so let's look at the formations. So this is Earth, this is me. I am falling on the Earth. I just hit the surface of the Earth. Well, things are elastic after this point. Okay, if this is the initial surface of the Earth. Now the surface will be deformed to have such a shape, and this will be the shape of me or the ball. Okay. So during this process, there are forces acting on the system. There will be a force acting on me due to Earth. And so there will be a reaction force acting on Earth. So again, the changes in the forces will be the same. The changes in the momentum will be the same. Momentum doesn't have anything to do with energy. Well, it is related, of course, through velocity and light, but the change in the energy doesn't mean momentum is changing, or the constancy of the energy doesn't mean the momentum is constant. So? Okay. How? Now, just imagine, okay, imagine this deformation as not the whole Earth, but the U, but divide Earth into small parts. They are so small that they will not be deformed. So this deformation that you are talking about here is just the relative motion of these pieces relative to each other. There is no deformation here. If this is moving downward in this deformation, but that means, okay, so this hit this one, this is moving downward, there's friction between these two parts. This is transferring momentum to this part, which will be moving downward, But at the same time, this will be slowing down, meaning it is gaining momentum in the upward direction. So even if these two parts are moving relative to each other, there will not be any momentum change. Okay, so we already had run out of past our break time. Just a 5-minute break, then we will continue.